Hello everyone. So hopefully today will be the last video in 2.2. 2.2 is a really long section. This is our 5th video if I'm not mistaken. So hopefully this one will be the last video. So last video we end up right here where we talk about theorem 2.2.4. So I'm going to show you why that is the case. So I want to show you a very simple proof to illustrate the reason being it. So let's suppose we are given a system A vector x equal to b with the associated homogeneous system A vector x equal to 0. We're going to let vector x sub h be the solutions to A vector x equal to 0. Therefore imply that if I multiply A by x sub h, I will get the 0 vector. We're also going to let vector x sub p be one solution to the linear system. That means if I take A multiplied by x sub p, I will get vector b. So now I'm going to let our solution set vector x be the sum of these two vectors. What I want to show is to show that this would satisfy this equation. Now what I need to do is to show that vector x equal to vector x sub h plus vector x sub p will satisfy the system. So how do I do that? Well, simple. I just plug it in. So let's say vector A times matrix A times vector x. That will equal to matrix A multiplied by vector x sub h plus vector x sub p. Now I know we didn't really formally go over properties of matrix multiplied by vectors, but here I'm going to tell you that I can actually distribute matrix A into both of these. The distributive property worked with matrix multiplication with vector. And what do we know about A times vector x sub h? Well, matrix A times vector x sub h will always yield the 0 vector. And what does vector A, matrix A times vector x sub p would always yield? That always yield vector b. Therefore 0 vector plus vector b would equal to vector b. Then that just show that A times vector x sub h plus vector x sub p will give me vector b. Therefore vector x sub h plus vector x sub p is a solution to the system. Except what I need to prove. Now what I want to do is to show you how using this theorem works. Okay? So show you a very simple example. Let's say given a simple matrix like this one. Let's say x minus 2y plus z equal to 2 and 2x plus y minus 3z equal to negative 1. The problem asks you to solve this system using theorem 2.2.4. Now, since the question specified that you have to use the theorem 2.2.4, you will not be allowed to solve the system using any other method. Okay? So how do you go about using theorem 2.2.4? Well, first thing you want to do is let's find x sub h. How do I do that? I have to find the homogeneous system, which is this one. that will form the matrix. What I'm going to ask you to do is to reduce this matrix to its lowest form. I'm not going to go through that process. By now, if you still don't know how to do that, you need to do more practice. You need to ask questions. You need to learn to figure it out. Okay? I mean, we went through 5 videos, and you have learned how to do this process in video number 2. And if you didn't do enough problems or try it out enough time to know exactly how to do it, you're not doing your part of the work, and I cannot help you with that. So if you do it correctly, this matrix will reduce down to this matrix. And therefore imply that x minus z equal to 0, y minus z equal to 0. Remember, in this case, the 2 1s are the leading entries. Therefore imply those 2 are the leading variable. That leaves z to be our parameter. And if I say move the z over on both of these, I'll have x equal to z, which is t. Y also equal to z, which is t. And z also equal to t, because that's what we let z equal to. And that come out to be x, y, z equal to t multiplied by 1, 1, 1. That is our homogeneous solution. Now, one thing I do want you to try out is take the coefficient matrix, which is 1, 2, 1, 1, negative 2, 1, 2, 1, negative 3. Multiply that by the direction vector, which is 1, 1, 1. Tell me what you got. I'll wait. Pause the video, go and give it a try. And don't wait for me to give you an answer. Go and try it out and see for yourself what the answer is. If you keep waiting for me to tell you the information that you need, you're never going to learn what you need to learn to do math. So if you do it correctly, you find out that it gives you 0, 0, as it should, because that's how we come up with it. So that's my homogeneous solution. So now here comes the difficult part. See, most students don't have issue with that, because this finding the homogeneous solution, students know what to do. They have a direct procedure that they follow, and that's how students like it. So they like to have a procedure. They like teacher to tell them this is exactly what you need to do. That way they can practice how to do it and get the correct answer. And that's why students hate finding x sub p. Because to find x sub p, what you want to do is what mathematicians refer to as by finding it by what we call inspection. What do I mean by that? Meaning that you basically look at the system. So here's my system. And try to come up with a solution without doing any major math. Now, that is usually difficult to do because, not because the math is difficult, because you require students to think. And that's what students don't like. Students like to have a set procedure and just simply follow the procedure. But here's what I'm going to tell all of you. If you don't like to think, you're in the wrong class. Everything in this class requires you to think a lot about different things that are related together that you need to make connection of. So if you don't like that, you are totally in the wrong class. Okay? So what I'm going to ask you to do is, once again, pause the video and look at this system and see if you can come up with some solution. A set of x, y, and z that would give you the correct, that will satisfy this system or this matrix equation when you plug it in. And most students in the class over the past 10 years when I did this come up with one of 2 solutions just by inspection, just by looking at it. So I'm going to go ahead and tell you to give it a try. So pause the video and give yourself a few minutes, and don't just say, oh, I'm just going to continue watching. No, pause the video and try to figure it out, because if you don't do that, you're never going to figure it out. So hopefully you spend some time thinking about it. Most students come with one of 2 answers. The first one that most of my students figure it out is this one. 0, negative 1, 0. To see that it works, all I have to do is just multiply by the coefficient matrix to see what happened to it. So the top will be equal to 0 plus 2 plus 0. The bottom becomes 0 minus 1 plus 0. That comes out to be 2, negative 1. There you go. That means 0, negative 1, 0 work. Usually also get a second one. Some student would have this one instead. 1, 0, 1. And once again, to see that it works, all you have to do is just plug it in. So that will be 1 plus 0 plus 1. And 2 plus 0 minus 3. So that comes out to be 2, negative 1. There you go. So those two are the most common one. Notice that the particular solution have some zeros in it. As a matter of fact, the reason why I have 0 in it because that's make it easiest for you to come up with the correct answer. Okay? If you try to figure out what 3 numbers will satisfy this equation, it's hard to do. But if you allow yourself to plug in some zeros in your particular solution, you'll find that it's a lot easier to come up with it. Okay? Now, with that being said, what should the correct answer be? Well, guess what? Depending on which x sub p you find out, you will have different answer. You could have this as your answers. That is perfectly correct. That is your right answers. Or you could have this one. That is also a right answer. Which one is more right? That's no such thing. They are both correct. Why? Because remember, parametric representation is not unique. So therefore, you could have different parametric representation that give you the same exact geometrical object that you're describing. Both of these solution set, both of these parametric representation describe the same exact solution set. That's why they're both correct. And as a matter of fact, if you did not see these two x sub p, but you find a different x sub p, then you can just stick it onto at the end and have your own answers. Alright? Now what I want to do is to give you another example. This one we're not going to do. If we have time during class, you can ask me to do this with you guys. Alright, so I'll leave you with this problem to try out, and then if you have the answer, definitely we probably go talk about during class, and if some of you have an answer, you can definitely share with the class, or if not, we can definitely go over it during class. So last thing I want to show you is this, and that will be the last thing in 2.2 that I want to talk to you about. And yes, 2.2 is have a lot of stuff in it. So therefore, that's the reason why you have to make sure you review your notes before you take your test. Linearly independence. That's the last thing we'll talk about. So if you recall that you learned a little bit about linear independence in chapter 1. From chapter 1, this is what you probably remember learning. If two vectors are not multiples of each other, they are linearly independent. Now, what's the important part about linear independence? Linear independence basically allow us to describe a geometrical object more properly. Now, why is that the case? So let me show you an example. Now let me show you this example. Consider the following. Let's say given 3 direction vectors. let's say vector u1 is 1, 0, 0. Vector u2 is 1, 1, 0. And vector u3 is 2, 1, 0. Now, if you think about it, if we use these three vectors to form a k-plane, what is these k-planes going to be? Now, if you think about it, you're probably thinking like, wait, we're three direction vectors, so wouldn't that mean that we're forming a three planes? And it might seem like it's correct, but it's actually not. Why? Because the following. Imagine the following. So imagine I'm going to define my three planes to be vector x equal to t1 vector u1 plus t2 vector u2 plus t3 vector u3 plus there's no direction vector, so I'm just going to leave it out. Wouldn't that form a three plane? And if you don't think too much into it, you think like, well, that does seem like that's the right answer, but it's not in this case. The reason why it's not, because of the following. Notice that vector u1 plus vector u2 actually equal to vector u3. Now, u3 is not multiple 1 and 2, but it's a linear combination of 1 and 2. That is the problem. So in here, notice that u3 is a linear combination of u1 and u2. Because of the fact that u3 is a linear combination of u1 and u2, it messes up our k-plane. How? Well, I'll show you. If I look at this right here, notice that I can actually rewrite my k-plane by changing vector u3 into u1 plus u2. Now, how does that affect my k-plane? Notice what happened. That means I will have t1 vector u1 plus t2 vector u2 plus t3 vector u1 plus t3 vector u2. And now I notice that I have two terms that have vector u1 in it and two terms that have vector u2 in it. So I'm going to collect them together. Notice now I only have two direction vectors. As a matter of fact, only two direction vector is needed in this case. The third one doesn't really do anything because it is a linear combination of the first two. Now, you might be thinking, like, wait, doesn't this still have three parameter because you have T1, T2, and T3? No, in this case, all I'm going to do, I'm going to rename them. T1 plus T3, that would just simply be some numbers. And we'll call that number S1. T2 plus T3, it will be just a different number, S2. Now, we only have two parameters and two direction vector. This actually form a two planes. The reason is because one of the vector that we use to try to form this k-plane is a linear combination of the remaining vector that we have, and therefore collapse our k-plane into a smaller dimension. In this concept is often referred to as linear dependent concept. In this scenario right here, we can say that vector u3 Because vector u3 is a linear combination of 1 and 2, we can say that vector u1, u2, and u3 are linearly dependent of each other, because we can actually form linear combination using of any one of these three by using the remaining two. That's called linear dependent, or sometimes called not linear independent, but I like to say linear dependent. Okay, now the question then comes down to, how do I define this concept called linear independent versus linear dependent? It's actually pretty simple. In this case, the reason why we have a linear dependence set of u1, u2, and u3 is because of this linear combination right there. But technically speaking, not just u3 can be formed as a linear combination of 1 and 2, but remember what we saw in chapter 1. Once you have a linear combination, you can actually rearrange this combination to form other variation of it. So to be more consistent, we actually go refer to this linear combination that we noticed, this relationship between u1, u2, and u3, to be this relationship. I can actually form a relationship where they equal to 0. And that become a way for us to describe linear independence versus linear dependence. So show you. So here's the definition. Let's say given a set of vectors. Let's say u1, u2, to uk. This set of vectors, u1, u2, to uk, are, actually I don't need the set if I will use plural. Let's say vector u1, u2, uk are linearly independent of each other if the equation a1 u1 plus a2 u2 plus plus a sub k u sub k equal to 0 vector has only one solution. And what that only one solution is a1 equal to a2 equal to a sub k. They all equal to 0. So they are linear independent. If I try to set up this equation to solve, and I find out the only answer I can get is 0 for all the coefficient, then it is linear independent. So now look at that definition. Now it makes sense, because if I put up this equation where I somehow add u1, u2, and u3 and try to get the 0 vector, I actually have a solution right here. I have to add 1 u1, 1 u2, and then I guess I can say plus -1. Maybe I should, let's see if I can clean this up. Oh, okay. Okay, let me just rewrite this. Okay. So notice that in this case, this basically forms the equation 1 u1 plus 1 u2 plus -1 u3. This would give me the 0 vector. So this equation has one solution. And that one solution is 1, 1, -1. So unless it's 0 or for all of them, they are linear independent. But if it's any answer other than 0, 0, 0, then it is dependent. That's how that works. Okay? So here, this equation, if I set this equation, set an equation. So I guess in this case, if I do set equation a1u1 plus a2u2 plus a3u3 equal to 0 vector, I know at least one other solution. One of the solutions is a1 equal to 1, a2 equal to 1, and a3 equal to -1. So that's why it's not linear independent, because of the fact that I don't have just one solution where all the coefficients are 0, but instead I have a solution that have some non-zero number in it. Now, one way to check if you indeed have a set of vector, one way to check if you have a linear dependent or independent set is to use this theorem. So this theorem will be tested. You will be asked questions related to this theorem on your next test. So make sure you understand. It's 2.2.11. And which says the following. Let's say given a set of vectors. Let's say u1, u2, to uk. Let's say we're going to form a matrix A. Matrix A is formed by using vector u1, vector u2, to vector uk as columns. So very important. We're basically using them as columns. So very important, to use this theorem correctly, make sure you don't make a mistake and use them as row. It would not work. You have to use them as columns. If the reduced matrix of A has a leading entries in every columns, therefore basically implying that every column is a leading variable. So the concept of leading variable and leading columns, leading entries, was in video number 2, in 2.2. So make sure you go back and look at that if you don't remember. So if every column is a leading variable, then this set of vector u1, u2, to uk are all linearly independent. So if the reduced matrix, every column is a leading variable, then the set of vectors are linear independent. If a column does not have a leading entry, or in this case, meaning if a column is not a leading variable, then that vector, remember each column represents one of the vectors in the set, that vector is a linear combination of the remaining vectors. Remaining that are leading variables. Okay, so might seem hard to understand what this theorem says, so we can definitely try a problem out and see. So once again, you're going to have to learn to reduce the matrix. So I'm not going to do the reduced matrix with you. I'm going to ask you to just simply do the reduced matrix on your own. Okay. So show you a very simple example. Okay. So here's probably a very basic example. Okay. Let's say we have three vectors. Let's say vector 1, u1 is 1, 2, 3. And vector u2 is 3, 2, 1. And then vector u3 is going to be 4, 4, 4. Now, it shouldn't be too hard for you to figure out that if you add 1 and 2 together, you get 3, just like the other example that we have. What I want to show you is what happened to this matrix that we form. So we're going to let A be the following. Let A equal to the matrix. Remember, we take these three vectors, use them as columns. So 1, 2, 3, 3, 2, 1, 4, 4, 4. So this is basically my vector u1 in the first column, vector u2 in the second column, vector u3 in the third column. What I want you to do is pause the video and go and reduce the matrix. Okay, once you finish reduce the matrix, you unpause the video and see the answers. Okay, so go for it. So, if you reduce this matrix correctly, you should have this. Notice that in this matrix, there are two leading entries. Right here and right here. Leading entries. And these two leading entries reside on these two columns. That would be vector u1, vector u2. So those two vectors are good. Problem, third row, a third column. This column does not have a leading entries. Therefore imply that this vector u3 is a linear combination of u1 and u2. Guess what? We already know that is the case because u3 equal to u1 plus u2. We already see that. So that's what this theorem does. So the theorem requires you to know how to reduce the matrix. And then once you reduce the matrix, you need to understand how to interpret the result. You will look for leading entries. You'll do exactly what I did here, encircle them. And then now, remember, every leading entry, once you identify them, they must exist in a column also. So identify the columns that they're in. And any column that does not have a leading entries becomes the vector that can be formed as a linear combination of the rest. And if you have a column that have no leading entries, that will imply that the set of vectors are dependent. Okay? Now, give you one more example to try out. So once again, because the video is already 35 minutes, so I won't be able to go over this one with you, but I'm going to ask you to go ahead and do them on your own and see if you can figure it out. So here's what the questions say. Use theorem 2.2.1 to determine if the following vectors are linearly independent or not. And here are the vectors. Oops. Alright, I'm going to leave it up to you to finish this problem, and you can definitely ask me to go over it in class if you want, or if someone can share the answer, that would be great. Alright, that's it for 2.2. I'll talk to you guys later. Bye-bye.